All right, so it's going to be recorded, and just in case you have some peers or friends that missed this lab, you can remind them that there will be a recording available sometime later today. It takes a few hours to process it. All right, let's see. So for today's lab, I just want to quickly explain the lab to you in case you have not looked at it yet. So for today's lab, we're going to look at this sort of this like a two-dimensional grid in XY direction, and then we have about 1,000 particles, and at time equals 0, we randomly spread them out on this grid, and the grid that we use has the X interval from 60 to 62 and the Y interval from 164 to 166. So it's 2 units in each direction. So you can think about, in this case, 2 meters. You can think about that, just how big the space is for the particle to move around. And then each particle is going to have a velocity in the X direction, in the Y direction, and given time steps, it's just going to advance. Every time step, in this case, is 0.5 days. Every time step, each particle is going to move a little bit in the X direction, a little bit in the Y direction. And it's going to reach a new location. And in the next half day, next time step, it's going to reach another new location. So those particles basically will be just moving around in this space that's available. Right. Now, you might have a question, could the particle move outside of the space? That's a certain possibility, but in this case, we don't really consider that. We just want to look at, okay, after 50 days, where's those particles at? What's the X position of those particles? So let's see. So this is at t equals 0. Now at t equals 50, we're going to have the particles probably somewhere here. This is T50, so we're going to have, for all the particles, we can look at all their X coordinates, we can get X50, and also all their Y coordinates, which is going to be Y50. So those are vectors that represent the X coordinates and the Y coordinates of all those 1,000 particles. And then we're going to let it advance even further. So after another 50 days, by the time time becomes 100 days, we're going to look at the X position and the Y position of those particles. At the end, what we're going to do is we're going to use the XY positions of those particles at time equals 0, time equals 50, and the time equals 100 to plot some graphs, some histograms, and then we're also going to compute the mean and the standard deviation after 100 days. So that's the sort of like the particle tracking model or particle walking model, the random walking model. So basically, you begin with the spread of those particles and then let it run over time, let the computer simulate. And then at a certain time, you record the XY positions. And then at a different time, you record the XY positions. Basically, that's how it works. All right. So any questions about the quick introduction? I know I probably didn't explain thoroughly, but any questions? All right, so I just want to quickly refer back to the introduction. So the formula for the advancement in the X direction is given by xt plus delta t. So this is the new position, new X position. This is the starting X position. So if it starts at this place in the X direction, and then it's going to, after a time step, it's going to increase some in the, or decrease in the X direction by following this formula. And then at the end of that time step, it's going to reach a new X position. Same thing with the Y. So those are the two formulas given. And obviously the velocity in the X direction, U, is given by Px, and the velocity in the Y direction, V, is given by this. And then we also have the dispersion coefficient D, which is given, and the epsilon and the eta in this case, they're just random distribution factors. It gives the particle a certain variation to move around in the location it is. So if a particle is here, then the epsilon and the eta basically is saying, okay, it has this possibility of moving around in the neighborhood randomly. All right. So, but this is a formula that we're going to use. And in order to use this formula, we're going to need those for the velocity, and then we need constant coefficients, constants. All right. So any questions? All right, then. If you don't have any questions, I'm going to jump into MATLAB and start working on the first part of this lab, which is to generate, let's go back, which is to generate this diagram. We want to know initially where the particles are. What's the at t equals 0? What is the distribution like? Right. So that's the first thing we're going to work on. But before we get that, so let's see, this is the new lab script. Now you should have a diary running. If you don't have the diary running, you can just work on the script, and then at the end, save the script, run the open the diary, and then run the script again. It should be more or less the same. It doesn't really give much difference. So this is the lab 3. And let's just quickly introduce the rand and rand-n functions. So in MATLAB, a rand is a random distribution, and the rand-n is a normalized random distribution, the normal distribution. Now the rand will give you random values from 0 to 1. So let's see. So rand gives random values from 0 to 1. So imagine you have a number line. So each time from 0 to 1, each time it picks a random value between 0 and the 1 there. So that's a rand function. And the rand n, which is a normal distribution, and it's going to give you value, but not necessarily give you value from 0 to 1, because for rand n, this normal distribution has a mean. It's a normal distribution with mean equals 0, and the variation equals 1. So what that does is going to distribute values randomly, but has an average that's going to be 0 with the variation. So if you're familiar with normal distribution, so it's going to give you this like a bell curve, which means more values will be picked randomly from on both sides of x equals 0. So there's a higher chance to pick values in that part, which is 1, -1. And then if we want to have values that bigger than 1, there's a less chance to have values between 1 and a 2 and a -1 and -2. So that's the normal distribution. When it picks a value, it emphasizes more values near the 0, because that's where the average is, and the less values as we move further away from the 0. We're going to have positive and negative, means just on both sides of the average of the mean. So that's a difference. So let me give you an example. So for example, let's say A is a vector equals rand. Let's just say I'm going to have 1 to 100. So this means first row 100 column, one row 100 columns. So we're going to have that will be my vector. So let me make this smaller and put this away. So if I run this part, let's just see, I'm going to highlight this and just say evaluate this in command window. So as you can see, it's going to give me 100 numbers, and all the numbers I have is going to be positive between 0 and 1. You get 0.8 0.88, and then you have 0.3 and a 0.1. So those numbers are generated randomly. So that's the rand function. And if I say I'm going to have a B, so this is a random distribution. And if I say B equals rand n, this is a normal distribution. That's from 1 row, 100 columns. So again, that's going to give me 100 elements. So I'm going to evaluate this. And now you can see with the normal distribution, I have some values are positive, some are negative, some are more than 1, less than -1, less than -2, close to 0. And so you get values that distributed in the positive and the negative x-axis, but then more values are concentrated towards the origin, well, x equals 0 in this case. So this is a normal distribution. All right. So in this example, we're going to end up using both. We're going to end up using both rand and the rand n at different places. So that's the first part. Now the second part, we're going to introduce subplots and histogram. Now we all know when we plot something, we just get one figure, right? But with subplots is that you can have one figure, but with multiple subfigures. So subplots. So the command is going to be subplot parentheses. There's 3 numbers here. So the first, let's just say we're going to have 2, 1. This one might, let's say M and P. So the first 2 numbers is going to tell us the sort of like the grid size for the figure. So M and N, so that's going to give us how many rows of figures and how many columns. So this is the M rows and this is N columns. So that's how we're going to arrange the figures. So if we have a lot of figures, we're going to put the first one in the first row, first column position, second one in the first row, second column position, and so on. So kind of like treat those each of the subfigures or subplots as like an element in a matrix, basically. So that's the first 2 numbers. And the P is going to be the position. It's going to tell us, is this going to be the first figure, the second, the third, the fourth, or the fifth in that matrix? So this is going to be 1, 2, 3, or so on. So that's a subplot. And I'm going to quickly use the example I have. So for example, I have A and a B, and I'm going to plot them. So let's just say I'm going to have subplot, because I'm going to plot 2 figures, A as a figure, B as a figure, but together in the same figure window. So let's say I'm going to have M, which is 2, and I'm going to call it 2 row 1 column, and the P is going to be the position. So the first one I'm going to plot, let's see. So the first one I'm going to plot is going to be the A. So the 2 row, the first row, first column. So in the, let me go back to this window. So in this case, I'm going to have 2 rows, 1 column. So the first figure is going to where the A going to be, and the second figure is going to be where the plot of B is going to be. So that's the subplot 2, 1, 1. So 1 is a position, means the first subfigure. And I'm going to plot the vector A. So I'm going to use histogram. And in this case, it's going to be A. And then it's not B. I'm not plotting A against B. So just A by itself. and I'm going to put 10 here. Now 10, so 10 is the number of bins in histogram. So if you're familiar with histogram, you can have a histogram that looks like this, right? So we want to know how many bins we're going to have. So in this case, we're going to have 10 bins. So that's what I have. Let's run this 2 lines. So I'm going to evaluate those 2 lines. And let's see, where's my figure? So here's my figure. So this is the A, the normal, the random distribution from 0 to 1. As you can see, all the values are from 0 to 1. And the y-axis is just showing us how many times does the number between 0 and the 0.1 happens, the 10 times. And then there's 12 times we're going to have a number between 0.2 to 0.3. And in total, but we have 10 bins. So from 0 to 1, we divide it into 10 intervals. So that's the first figure that we plot in the subplot. And then the second one we're going to have is we're going to plot B. So subplot 2, 1. So again, it's still 2 row, 1 column arrangement of the figures, but it's a second figure that we're going to plot. And in the second figure, we're going to plot, again, it's a histogram. And this time I'm going to plot B. Again, I'm going to use 10 bins. So let me run this second part. And my figure is here. So the bottom one is the normal distribution that we picked randomly. And as you can see, it's still 10 bins, but it's going to give me values around 0. So 0 to 0.5 and the 0 to negative 0.5 that tend to have more values if you kind of look at this histogram as a bell curve. Let's just say I want to change the number of bins. I want to change it to 20 bins for the second part. So let me rerun this. As you can see now, it's going to divide the interval in the x direction, between well, whatever the lowest and the highest, it's going to divide the values into 20 bins. So it'll be 0. I think it's 0.25. Let's see. Actually, I'm not sure. But anyway, so that's 20 bins for the histogram. All right. Any questions about those introductions about the random value and then the random distribution and then the subplots as well as histogram? Any questions? All right. If you don't have questions, we're gonna really work on the first part of the lab. I know it's been taking a while. So let's see. Lab 3, part 1. So the first thing we're going to do is we know that there's going to be 1,000 particles that are going to be distributed. And then we're going to have the time step, which is 0.5 days. And then we want to plot, let's see, where was it? Yeah. So basically we want to generate this plot for t equals 0, right? So if you look at the plot, the bottom left corner is starting at x equals 60, y equals 164. And then the x interval goes all the way to 62. And the y interval goes all the way to 166. So basically 2 units in each direction. And we want to distribute, before we do anything, we want to distribute all the particles uniformly on this grid. So in this case, we're going to use rand instead of random. So let's begin with, so I know that's going to be n particles. So that's going to be one solvent particles as given. And so this is a number of particles. And then we also going to look at the initial position in the bottom left corner. So XC, we're going to see that's equals 60. Was it 60? Yep. So that's going to be 60. So this is a bottom left X position. And then YC, it's going to be the Y coordinate of that position. So that's going to be 164. So this is a bottom left Y position. You can think about that's the sort of the bottom left of the grid. And then what we're going to do is, let's see, do we have a X position? Yep, we do have it. All right. All right. So now what we're going to do is we're going to say X0 equals 0. So this is a X position. You know what? I'm not going to type this there. I'm just going to not type there. So now we're just going to randomly distribute 1,000 particles within that 2x2 grid. So I'm going to say X0, the position of X at t equals 0. That equals XC, the bottom left corner position, plus whatever the random distribution I have, which is going to be rand. It's going to be 1, and then it's going to be 1 row, and then the number of particles. But if I just do that, remember that random distribution is only going to give us, so rand is only going to give us from 0 to 1. So if I pick values, it's only going to be somewhere there. And if I start with XC equals 60, it's only going to go from 60 to 61. That's not enough. So what I want is I want random values from 60 to 62. So I'm going to actually take the random distribution, multiply by 2. So that will randomly distribute between 0 and the 2. So that will be 2 times rand. So that will give us random values from 60 to 62, because the starting value is XC 60. And we do the same thing with the Y random positions. So Y0 equals YC plus 2 times rand 1, again, number of particles. So this is a X0 is position is X position at t equals 0, and Y0 is Y position at t equals 0. So that will give us a random distribution of particles along the X direction 2 units from 60, and along what the Y direction 2 units from 164. So that will give us basically the XY coordinates of those particles in the grid. And the next thing we can do is we want to plot it. So let's see, we're going to plot. So let's see. Plot initial position. And because we're going to plot the initial position and also t equals 50 and a t equals 100, so we're going to use subplots. We're going to use 3 subplots. So let's see, we're going to have, I'm going to call it figure 1. And subplot. Now this at t equals 0, I'm going to plot the figure in the first part of the figure. So subplot is going to have 3. So it's going to be 3 rows, 1 column. In this case, this is the first figure we're going to plot in the subplot. And then we're going to plot x0, y0 against y0. And the color, I'm going to use black. And that should give me the plot. So let me run this part. So I want to evaluate this. Oops, xc with xc. Did I not define xc? Oh, I said xc. Oh, I didn't include the xc. Sorry. So let me run this whole thing. Part 1. All right. So that's what it looks like. So basically, it randomly generate 1,000 particles and distribute them in the x direction from 60 to 62, and from 164 to 166. All right, here's a question. So MATLAB does not recognize my B. Let's see, Marcus, did you have like a rand n? Okay, so if MATLAB give you if you type rand n and it doesn't plot the function, that might be something with the MATLAB program that I can take a look at that later. It might be something involving like installation. That might be something missing, but usually that shouldn't happen because rand n is sort of built in MATLAB language there. So it's is it okay if I take a look at that later? All right, so my plot drew lines all between all 100 points. Is that a way to just place points? Let's see, same with mine. That's interesting. All right, let's try something. So plot x0, y0. Okay, so if you get something like this, right? It has like a sort of have all the points, but draw lines connecting them. Now, in that case, make sure you add this b dot at the end. So you're going to use this part, the specific part that. So b dot means just, it's going to be black and it's going to be dots for points. I think it's black. Maybe I'm wrong. Let's see what b. Evaluate this. So if you use the b dot after x0, y0, and that should fix the sort of like the line problem. Oh, black is k. Okay. K dot. Okay. Thank you, Will and Leighton for pointing out. So B is blue. Not getting my color right, and the K is black. But so that will give it the color of the dots, and then the period right after that, that's going to give it like the actual dots, not like a connected points. Okay. Were you able to fix the problem? It doesn't matter in this case. I just use K or B, just a color. Good. So thank you. All right. So I'm just going to add the note that this period is, let's see, gives the dots not connected. So that's the first part. Now the second part, we're actually going to do the random walking. So we plot the position at t equals 0. Now we want to know, okay, we're just going to let it advance 0.5 days each time. And we want to know, okay, 50 days from now on, where are the particles? And we're going to plot that. So this is, let's see, lab 3, part 2. We're going to say random walking to t equals 50. And we're going to use the formulas given in the introduction. So the x of t, y of t. But before we use that formula, we have to define a few constants and the variables. So we know that the constants given are dt, the time step equals 0.5. So this is a time step equals 0.5 days. And then we also have this dispersion coefficient, capital D, and that's going to be given 0. Those two values are given 0.001 meter. So this is a dispersion coefficient. That's a 0.001 meter square per day. Oops. And then we also have another constant, which is a p in the velocity. So I'm just going to define it here. P is equal to 0.003. Though those values are given. So this is velocity constant. So now we define all those constants. We can start figure out what the velocity in the x direction and the y direction are, because we need them for the formula x of t plus delta t, y of t plus delta t. So the velocity, let's see. So velocity, we have x, not x, sorry, u equals p times x. This is the velocity in, let me just double check, make sure I'm not giving you anything wrong. U p times x. Velocity in x direction. And as you know, I have not defined what x is yet. Velocity in x direction. And the v is going to be negative p times y. This is going to be velocity in y direction. And I need to tell the computer what x and y is in this case. Now, before I do anything, my x is just going to be x0. So x equals x0 and y equals y0. So we're taking the initial position, set it as x and set it as y, and then we're going to use them to do the walking, to calculate the velocity and then to calculate the position. All right, so that's the two velocities. And then now I have everything. I can write down the new position based on the position we begin with. So this new position is going to be x, the new x, in this case, we're not distinguish them. So the new x is equal to the original x plus u times the time step dt, and then plus parentheses, we have square root of All right, you know what? Nothing works well this morning. My headphone is dying too. Oh my goodness, where's my? All right, give me a minute. I'm so sorry. My headphones are dying. Oh, yeah. All right, I just need to find that cable to charge my headphones before it dies on me. Thank you. Okay. All right, sorry about that. What a mess this morning. So in the square root, follow the formula. We have 2. Yep, so x zeros and the y zeros are vectors from the initial position. So that's what we're going to use. So we have the 2 times the dispersion coefficient times time step dt. And that's underneath the square root and inside the parentheses. And outside, we're going to have an epsilon. In this case, we're going to use a normal distribution because we want each particle to have the freedom to move around. So times rand n. And in this case, rand n is going to be the number of particles. So that's going to be, let's see, 1 number of particles. Now you could just rename it epsilon and eta, but in this case, I'm going to be a little bit lazy, just call that random n for epsilon, and the eta is the same. So that's the x position, and the y position is going to be y plus v times dt time step plus, again, basically the same expression we had earlier. In this case, we have square root of 2 times d times time step dt, and then we multiply by eta. Again, it's going to be a random distribution. I'm sorry, it's a normal distribution. So rand n, 1 common number of particles. So this is a new x position. And the second one is going to be new y position after each time step. All right, does that make sense? So now we have a problem. If we just run this, we're just going to get to the next time step, right? We're not even going to advance over time. We just get, okay, starting with x0, y0, we got, okay, at t equals 0.5, where we end up with to be. We don't want just to complete one time step. We want to complete a lot of time steps until t equals 50. So we need a full loop for this part. So everything, velocity will change based on time because the velocity depends on the new position each time, and the new position also changes. So we're going to put this part in the full loop, but the initial x, y, they don't change based on time. They just the starting x, y position. So we don't put that in full loop. So in this case, we're going to use a full loop. So for t is from 0 to 50 with a time step dt 0.5. And the U is going to follow this. This equal to P times the position. Velocity in the Y direction is going to be -2P times the Y position. And then the new X is going to be given by this formula. The new Y is going to be given by this formula. And that should be the end of our for loop. So it's going to be, for t equals 0, it's going to go through this part, calculate the velocity and the position, and then advance one more time step. T equals 0.5 is going to go through this, and the t equals 50 is going to go through this. At the end, we just have one x vector and a y vector for the final position at t equals 50. So we're going to say t50, sorry, not t50, x50 is equals x, the x value we get from the for loop at the end, and the y50 is equal to the y value we get from the for loop. So x position at t equals 50, and the second part is the y position at t equals 50 days. Does it help with this problem? I know we're kind of running out of time. I'm almost done with this part. Does that kind of help with this? Any questions? Okay. All right. So from here, what we're going to do is we're just going to plot this in the subplot. We already had a subplot created, so we're going to say subplot 3 row 1 column. In this case, this is going to be the second figure in the subplot, and we're going to plot the x50 against the y50. And in this case, what did I use? I think I used black. It doesn't matter. In this case, I'm going to use blue then. With a dot means we want points. So that should give us a plot. So let's run the second part all together. Evaluate selection. And if you do everything correctly, and then you probably end up with something like what I had. So we still have 1,000 particles, but now the particles are sort of like distribute in a different way. So that's the second one. All right, any questions? For the next part, so let's say lab 3, part 3. For the next part, what we want, we're going to basically take the same particles, the same setup we already got at x50, y equals 50. And then what we want is we're going to continue this, but generating more generate more distributions from t equals 50 to t equals 100. So what you could do is, again, just write a for loop in this part. So for t is from, because we already have 50, let's say 50.5 with time step dt to all the way 100. And basically everything you do in this part is the same thing we did in the second part. And then that should give us a new plot. So that will give us a distribution. And then I think the next part, we don't get to it, but I think it's manageable with the histogram because you already have the x00, x0, y0, x50, y50. And then you have you're going to have x100, y100 from this last part. That should be enough for you to complete the histogram. Any questions? I know some of you might have to go, but I just want to add one more thing. If you look at what I had, I only have 2 subplots. I don't have X label, I don't have Y label, I don't have title for each of them or any of that. So how do we add those titles to distinguish them? So what we do is when we plot the first subplot, if you remember, we plot this over here, plot the initial position. So over there, what we're going to do is we're just going to add the X label, the Y label, all those information, just like we did with the normal figure. So if I add X label, and after this, I'm going to stop talking. So X label, I'm just going to say is X position with meters as a unit. And Y label is going to be Y position meters. And I'm going to have a title. I know there's a questions. I'll just get to it in just a minute. So title, I'm going to say particle distribution at t equals 0. So if I rerun this part, I should have those added. As you can see, I have X position, Y position, particle distribution as the title. And you do the same thing with the second subplot. You add it right after you plot the X50, Y50, and then that should give you this. Okay, yes, Marcus, I'll help you. All right, so I'm going to stop there. I apologize for many things this morning, and hopefully that will give you started on this lab. And if you have any questions, let me know. Like I said, I'm going to have office hours like right now, and it's going to be on Zoom, so you don't have to go anywhere if you need help. And later on, I'm going to have office hours again. I'll help you, and if none of the time works, just let me know. All right, everyone. We're going to meet in person next week. I apologize for the inconvenience, and I'll see you around. If you don't have any questions, feel free to leave. But if you have questions, definitely stay.
Thank you.
All right, take care. Let's see. I'm going to